it's my pleasant task today to try and take you out to the boundary of everything that we can see and beyond. You may realize that everything that we know, all information we get, is subject to a restriction. That restriction is that there is an ultimate speed that we have never figured out how to get behind, and it is built into all of our physical law, namely the speed of light, the ultimate speed at which information can flow. What that means is that when we look out, we look back in time to times that are extremely early, but we are bounded by what we can see. What we are not bounded by is human thought, and human thought allows us to go beyond that which we can see to project what may be far, far beyond what the universe looks like in the ultra, ultra, ultra large, as opposed to the little bit that we can see, which to you seems very vast. Before we start on that adventure, I want to give a quote and use that as a way for us to be here and now and understand what structure is in and what the universe is made of. So Walt Whitman, to me, every hour of the light and dark is a miracle. Every cubic inch of space is a miracle. So imagine yourself, we all, being outside, bathed in the light of the sun, and a teaspoon, which is almost a cubic inch, and what actually is at any one moment in that teaspoon. Of course, you know it's oxygen and nitrogen. That is the stuff, the oxygen being what we breathe. And if we talk about the amount of energy or mass, there is about 1 unit of atomic mass unit in every nanometer. Very tiny. But there's other stuff there, and we know it's there, and I'm going to tell you a tale, partly how we know it's there. We know it's there from the light that comes to us from the ultra-early moments of the universe. And what have we learned about? We learned about the dark nature of the universe. First, the light. So in every teaspoon, apart from this ordinary matter, which is anything but ordinary, there is cosmic radiation that comes at us from the Big Bang, and there are about 400 of those in every cubic centimeter in a teaspoon, some number of thousands of those. As well, there is another kind of effective radiation that also comes from us in the early moments of the universe. Those are called neutrinos, which just zip through our body without interacting, or interacting a very little bit. There are also gravity waves, little wiggles of space itself, but that will not be a topic because there's hardly any energy in that, although it's one of our great things to try and find it. What we have learned, though, is that fundamental to the fabric of the universe are dark things, dark matter, dark energy, not very imaginative names for such magnificent things. Dark matter is what holds the galaxies together and therefore allows us to be here and now. There is about 1 unit of that atomic mass on average in the universe in each cubic meter, so not very much. It collapses when the galaxy forms, and it collapses by about 10,000. So there would be a more or less 1, depending upon the type, of these mass units in every teaspoon. We are trying to find them on the Earth in deep mines, and we may succeed. But that's another story. The dark energy is more mysterious yet. It is a potential sort of energy that exists everywhere in space, and it does not compress, but it is now controlling how rapidly the universe is expanding. It is causing an acceleration. It is intimately related to what we call in physics vacuum, which brings to mind nothingness. but it is decidedly not nothing, because what happens in this thing we call the vacuum is that the properties arise to make the mass of everything that is our mass in the hydrogen and the helium and the oxygen and the carbon that holds us together. And that is, in fact, what the CERN accelerator in Geneva is trying to find and has now found an aspect of this energy. There are other possibilities, which I will pass over for the moment and take you on the beginnings of our journey. And I'm going to begin with a figure, which is looks like a football, but it's in fact to represent the entire sky, with this being the North Pole, this being a South Pole, but not of the Earth, of our galaxy, and these white things here are stars within the Milky Way galaxy, which you may know as a disk galaxy. We live about maybe a little less than a third of the way out in the Milky Way galaxy. It's a spiral galaxy. And this remarkable thing shows a painstaking thing that was done over a couple of years in the 1950s, where a team of people were putting dots on this structure to represent 7,000 galaxies, and they were also painting in, 7,000 stars, and they were painting in stars that were that sort of milky essence called the Milky Way. But that, but that misses the thing that's holding the Milky Way together that was not actually discovered till much later, which is that around the Milky Way, there is this dark matter that starts from way out here and goes all the way around and is the stuff that holds together all of the stars and other things. And that was an amazing discovery. And relative to the amount of ordinary matter in space generally, the dark matter is about 5 times, and that factor of 5 is what means that it has control over the gravity. I'm showing you this, which is another picture of the Milky Way, showing all sorts of emissions and all sorts of wavelengths that occur in this beautiful kind of picture, mainly because I want to focus on this earliest light that's way up there. But the Milky Way is emitting in all sorts of wavelengths, and it is very, very active in hot grains of dust that are radiating. It's a very beautiful picture. And anything that you might... Okay, so emissions in the Milky Way. Now, if you look at this, you must say, that is complicated. And it is. You cannot describe all of these emissions by a few simple numbers. And what is most remarkable is that at some level you can derive all of that complexity from just a few simple numbers. And we learn about those numbers by revealing information up here in these tiny little red and yellow bits, which is an image of the primordial radiation. So just within the past 2 months, we released information about this that took the media by storm. And I will describe that in a moment. We revealed this, which is an image of the universe when it was 13.8 billion years ago, 380,000 years after the Big Bang. All of these little things are little increases and decreases of temperature measured in microdegrees, really infinitesimal, and it's got what looks to be also a complex pattern. But the information in that pattern is actually completely defined by a few numbers which we can measure. And I will describe this in much more detail as we go. But what I want to do is to bring the idea of scale into focus here, because I'm going to take us to the universe when it was extremely small. So the current scale we can measure by an exponential to the 0th power, 1. That is measuring a scale relative to it. If we go back when this radiation from the earliest moments in the universe was released, the universe was about 1,100 times smaller in terms of the region across. And what that means is that its density was about 1,000 cubed times heavier, namely 1 billion times denser. But what we're going to use as our number here is an exponential idea, a logarithm. It is 7 e-foldings, we call it. And so we've gone back to 7 e-foldings from the time now to when this radiation was released. And that will be an interesting number as we proceed. Before I do that, I want to show that the complexity is not just the Milky Way. As we break out of the Milky Way in a painstaking way and have learned about the structure of the universe, as we marched our way out towards this distant time when the universe was 1,000 times smaller, this shows a complex pattern of each one of these things has, for example, this is hundreds of thousands of galaxies in it, and you can see that they're all in these kinds of blobs. They're called superclusters, and it looks like there might even be interconnectivity among the superclusters. And we can look at the universe on this scale, and out here it was about 10% different than here in terms of being slightly more compressed, not even close to that factor of 1,000. And we observe galaxies out to a time when the universe was in these units 2 times, more than 2 times smaller, about 1/10 of the size. And there were no galaxies whatsoever when the universe was about 1/20th of its size. So there is a time before the galaxies, before any possibility of the beginnings of humanity. Humanity occurred much later, as we shall see. What is amazing is with the information that we've gotten, we can actually simulate the universe. And there is a simplicity of the microwave background radiation, the first light of the universe, which is this pattern. And the pattern may look complex, but as I say, it's characterized by a very few numbers. But what we can do is we can put it into a very large computer here at the University of Toronto and work forward under the laws of gravity and the laws of energy being radiated as ordinary matter comes together. And we can say, what will it look like? Just starting with a situation with just a few numbers, and it'll look something like this. This is about the size of the region that we saw with all of those superclusters in them. And each one of these things here is associated with that superclustering form. And so there are various elements associated with this. And what is amazing is how well we understand this. We do these great surveys of galaxies, and we look at the way things are, and it works incredibly well. So we have understood the passage from this stage when the universe was 1,000th of its size and was simple to this stage when the universe was complex. And we have learned this under mainly the action of gravity acting on dark matter with this dark energy that I referred to being an important ingredient. And the simplicity of the period when the universe was 1,000 times smaller allows us to be very bold and make an extrapolation back to arbitrarily earlier times. And the universe must have been simple then to have been simple when it was 1/1000th of the size. And so we can actually extrapolate back to a time when the universe was a 50th, a 10 to the 50th smaller in terms of its scale across, unimaginably dense. And this shows a picture of calculations we can do to actually capture that remarkably early era. Okay, so how did all this come about? It basically came about because of the information that was carried to us by the first light of the universe that was released when it was about 1,000th of its size. And it made headlines, and the number that I'm going to tell you about, which I find quite remarkable, is when we released this, if you Google Planck satellite 2013 results, information released on March 21st, you get about 1 million links, which shows that people really care about the ultra-early universe, I think because it takes people beyond the day-to-day, and you look into the, you get to look up, look back, and get into a truly awesome story about the evolution of the universe and what humans have been able to do with advanced technology and the theories that we have that drive that technology in terms of what we look for. Okay, I will not describe in detail how we get those 7 numbers, but what we have here are these little tiny ups and downs of this temperature which encode the information which is in 7 numbers. And we learn all about what the universe is made of and how much of different things there are, which I'll also pass on, and talk a little bit about the structure of the ultra-early universe that we learn. 2 of those 7 numbers are characterizing that ultra-early structure. And what was amazing, and what physicists who saw the data that we released 2 months ago were quite excited about, was that, wow, it's only 2 numbers. And that characterizes this ultra-early time in the universe. The fact that we can even think about such a time is amazing. And there's still possibilities for more complexity in the ultra-early universe. There are these regions which we call anomalies that might indicate complexity, but I'll skip over. Because what I want to do in the few seconds remaining is to say that what we have done or what I've done in this talk is to take you from this region in the early universe through to, by computation, into this time when the microwave radiation was released, to this period where we have the complexity of the cosmic web around this, and in some location here will be the galaxy and ultimately the Earth forming in it. But we can use the same laws of physics to go backwards in time to an ultra-early thing far beyond the region that we can see in the universe to speculate on what it looked like. And that speculation has led us to think that we are dealing with an incredibly vast place, the universe, and that we can do it with some confidence, because the laws of physics here seem to be the same as the laws of physics there. And so the story that I've taken you on is a series of events that occurred from the ultra-early moments of the universe through to here and now, in which we have the creation of matter, light, etc., formation of the Earth, to now. And so I will end on 2 notes. We shall not cease from exploration. And the end of all of our exploring, namely from there to here, will be to arrive where we started and know the place for the first time. That's T.S. Eliot. And, whoops. And the last thing I will leave you with is, given this vastness, given the ultra-large scales of the universe, what is the Big Bang? There is no Big Bang. That is our current view. That is a view that very few people know. There is no Big Bang in our current understanding of the evolution of the universe. There is what you might call a whole series of little bangs that were essential for us to have been created when the universe perhaps was as small as 67 of these E-foldings earlier. And that's when matter and radiation formed. And most of the volume in the universe, we think, has never gone through such a phase. It is far, far vaster than any vastness we can imagine. And then as we look to the future, we also see that there is no likelihood that we will have another bang. We will just keep expanding and expanding and expanding, and I'll end there.